Okay, so good afternoon, welcome to this presentation. I'm Fabrizio Pece, and I'm a postdoc at ETH Zurich. Today I will talk about MagTics, a recent joint project with LMTS Group, an EPFL group that specializes on soft actuator hardware. MagTics stands for Magnetic Haptics. It is a haptic device whose form factor is small enough to allow its usage in a variety of wearable and mobile settings. Before walking you through the project, let me give you a little teaser of on the actual device. So please pay attention to these white pins, as they are the MagTics actuators that lay at its core. So MagTics is a small and flexible haptic device which combines the fourth generation capabilities of hard actuators with a soft 3D printed case. The flexibility and thin form factor of MagTics allows it to be used in a variety of interactive scenarios. For instance, MagTics can be mounted directly on skin for mobile notification or attached to any surface, turning non-interactive objects into interactive devices. MagTics can also be used to reproduce coarse tactile feedback for VR. Haptic feedback has become a central aspect of mobile interaction, and in fact it is often used in wearable and mobile settings to combat the visual attention scarcity problem. However, traditional approaches are limited to flat and often rigid arrangements which cannot conform to arbitrary body shapes. Nevertheless, mobile haptic feedback is a very well-studied area of research, and especially in the vibrotactile area, there has been a lot of work, such as solutions to convey feedback in several parts of the body, such as the waist, the finger, or the wrist. However, vibrotactile actuators cannot use coarse, non-localized stimuli. In order to provide richer, localized tactile feedback, direct stimulation on the skin has been used. For instance, researchers have explored solutions to convey tactile feedback in mobile interaction, in virtual reality, but also for shape exploration. However, as you can see, tactile feedback has so far been limited to mechanically complex, flat and rigid designs, which often equate to large power consumption. So from this is clear that while localized tactile feedback is the type of feedback that we would like to have for wearables, it is also very clear that it's challenging to make it flexible. The reason behind this are twofold. So if we want to use soft actuators, then we have to keep in mind that this deform on impact rather than imposing a deformation on the wearer, and this results in weak contact forces. On the other hand, if you want to use hard actuators, these need to be in constant contact with the skin, and they have to move together with the skin. So unless we don't wrap them very tightly around our skin, thus limiting the movements of the users, it is very hard to have them conform to arbitrary body shapes. So our solution then is to place hard actuator cells into a soft 3D printed case. This generates the force of hard materials while keeping the wearable properties of soft shells. Okay, so now we can move on to the actual device principle of operation. And we've built a series of functional prototypes that we've used during our evaluation and application scenarios. Each of our MagTics prototype contains 4 actuator cells with a diameter of 1 centimeter. These are embedded in a soft case. On top and bottom of each actuator cell, we mount a pin with a stroke of 2 millimeters. However, these strokes can be made different by simply 3D printing different pins. Each actuator can move in both directions and requires very low energy consumption due to our novel actuation technique. The cells themselves contain a small permanent magnet which gets attracted to either side of the device, holding its position without requiring any additional power. The rigidity of, and thus the strong forces in MagTics is given by the hard actuator cells, while the soft feeling is achieved through flexible printed electronics, also known as PCBs, and of course the soft 3D printed case. Now, each individual actuator cell contains a shielded permanent magnet, which is sandwiched between 2 PCB coils and 2 latching plates. Now, the latching plates here are responsible to lock in place the permanent magnet to either side of the device. So as the magnetic force is roughly proportional to the distance between the magnet and the latching plates, when the magnet gets nearer to one of the 2 sides, it is essentially attracted to the border and the latching plates locks it in there. So a taxel will remain in either positions, consuming no further power. We will now look at the mechanism which is used by our device to move the taxels, to actuate the taxel in one of the two states. So the magnet that you see in figure here is latched to the down position. And no further current is required to keep it in that stable position, as the latching plates attract the permanent magnet and keep it locked to that position. However, if we now apply a short current pulses of 10 to 20 milliseconds to both coils, we will generate a magnetic field in the bottom coil that repels the magnet, and a magnetic field in the top coil that attracts the magnet. This will result in a net force that will basically break the latching at the bottom, push the magnet up, and create a new latching at the top. At this point, the magnet is locked in place, and we don't need any more current, producing an holding force that varies between 160 and 200 millinewton. These holding force are sufficient to keep the pins in place, the actuator in place, even when the skin is pressing against them. So multiple of these cells form an array of taxels, so form our MagTics, and this can be controlled independently using the latching mechanism that you've just seen. Top and bottom coil, though, are operated simultaneously, but with opposite current direction. So if we want to switch a taxel from up to down, all we need to do is to pipe current in one direction. And if we want to switch a taxel up, all we need to do is essentially reverse the direction of the current. So assembling MagTics is relatively straightforward, and one device can be typically assembled in minutes. The fabrication time is bounded by the printing time of the soft case, essentially. Here you can see my colleague Juan, which is assembling one unit, and first he lies down the PCBs, to then put the actuators in the case, and then he puts down the latching plates. Finally, a heat sink is installed to essentially obtain the final device. So to demonstrate the capabilities of our device, we have developed a series of interactive scenarios. And before moving to the actual application, I would like to take a step back to illustrate you the type of actuation modes that our device can afford. So MagTics can afford two main types of actuation modes. The simplest mode is the static mode, and in this mode, either a single pin or a multiple pins are actuated together. So in the single pin case, an individual taxel moves from its current position to the next and keeps that position. Now, please pay attention that this video is essentially looping, but actually the taxel will stay in the up position. In the numerical case, though, consecutive taxels move from their current state to the next to render a number. And in this case, for instance, we are rendering the number 3. A richer actuation mode is given by the dynamic mode, and here taxels are actuated in sequence to generate a sense of motion. So in the single pin directional case, following one direction, consecutive taxels move from their current position to the next to eventually come back to their original position. So you can think of this as a sort of wavefront that moves from one direction to the other. In the numeric directional case, once again, following one direction, consecutive taxels move from their current state to the next, and they hold this position. So in this case, you can think of this as a power bar that feels from one direction to another. So this set of actuation modes, then, are the building blocks of our applications. And the first set of applications we're going to be looking at focuses on wearable scenarios. So when mounted on the wrist, MagTics can render various notifications directly on the skin, such as messages or incoming calls. MagTics can also be beneficial while performing mentally engaging activities, for instance, while training. And our pins have asymmetric actuation, which means that they can actuate in both directions, and this allows also users tactile exploration. Due to its flexibility, MagTics can be mounted on any surface, including curved surfaces, and to showcase this, we have developed a second set of applications that focuses on augmenting the interactive capabilities of existing objects. So MagTics, for instance, can be mounted on input device to extend their output capabilities. And for instance, this can be used to physically render hyperlinks or other UI menus, such as drop-down menus. But also numerical quantities can be rendered with our device, for instance, search hits in a web page. When attached to everyday objects, MagTics can enrich their affordances, for instance, allowing a mug to signal an incoming call, or a bottle to remind the user to drink their daily water intake. Finally, we also have developed a simple yet effective tactile feedback for VR, and as our actuators can be switched at an interval that go as low as 0.01 milliseconds, seconds, our device could be used to render different feedback stimuli. So here we show the device worn on a finger to enable feeling of virtual objects, and as the real hand moves through the virtual scene, the taxel corresponding to the colliding bone are essentially actuated. Besides developing application for our device, we have also conducted a user evaluation of our prototype to characterize it and inform the design of its future application. So initially, we have tried to understand which body locations are better suited for MagTics placement, but also which actuation period range is the one that is perceived and discerned better. By actuation period, we intend the time elapsed by 2 consecutive moves of a pin. So to answer these questions, we have run an exploratory study, testing our device in 6 body locations and considering an actuation period range that goes between a second and 0.05 seconds. We consider both static and dynamic actuation, and we measure the accuracy in discerning pattern. So from this initial study, it emerged that the location with the highest sensitivity and discernibility are the upper arm, wrist, and finger, and we identified the best period range in the range of 0.05 to 0.5 seconds. We also discovered more complex details on the type of pattern. For instance, we found out that dynamic patterns perform the best on the arm and on the finger, or that static pattern performs the best on the finger. However, there is more to this, and I encourage you to look at the paper for further details. Anyway, once we narrow down the body location and actuation range, we have run a final, more comprehensive study. And in this case, the goal was to further understand the effect of placement and actuation mode on user accuracy and discernibility. So once again, we have conducted a user study that this time focused only on 3 body locations, the arm, the wrist, and the finger. And we fixed the actuation period to 1/4 of a second. We used a similar procedure as before, so we actually consider static and dynamic patterns, but also a combination of the two. And again, we measured accuracy on pattern recognition, but also users' time to react. So regarding the accuracy, in general, the 3 locations performed similarly, with the wrist obtaining slightly better results on average. However, from the results, we found out that there's a significant effect of mode on accuracy, with the dynamic patterns performing consistently better than modes that rely only on pin localization, so the static modes. We also noticed the high accuracy of static patterns on the finger. And this is a particularly interesting result because essentially it suggests us that highly localized patterns, such as the numerical pattern, can be discerned, and so the feedback can be conveyed without the need of basically encoding this into repetitive patterns, such as is the case of vibrotactile feedback. So this could be particularly useful in applications when the mental bandwidth it's limited, for instance, during sports. Response time was also positive, with again a significant effect of mode, and the dynamic mode once again scoring consistently better than the others. Please note that in here, lower means better. So, to summarize the results of our studies, what we discovered is that our device scores a high accuracy on pattern recognition, with dynamic being the best actuation among the types. The best locations in terms of accuracy and discernibility are arm, wrist, and finger. And our device performed the best when operated in an interval range, in an actuation period range in between 0.05 and 0.5 seconds. Also, we found out that numerical patterns scored an high accuracy on the finger, meaning that this type of highly localized feedback does not require pattern encoding, as is the case for vibrotactile feedback. So we also record some answer to questionnaires, and based on these results, we actually we found out that participants felt more confident when using our device either on the wrist or on the finger, suggesting that these 2 locations are perhaps the better suited location for MagTics. Participants' comment actually echoed this, with users suggesting more frequently application that had to do with the sports domain, such as wristbands for while running, or a wristband for basketball to keep track of fouls or points, but also directional gloves for biking. Someone also suggested more utility-oriented applications, such as a wristband that could keep track of the remaining balance on your bank account when doing contactless payments. So our experimental results and application indicates that MagTics is indeed a very good and promising first step towards rich and soft, flexible wearable haptics. However, there is obviously ample room for future work. And first, our prototype requires short pulses of 130 watts to operate, generating excessive joule heating during repetitive actuation. At the same time, though, the thick rubber that we use is not efficient in its dissipation, and this essentially sometimes leads to pretty bad failure cases, as you can see in here. Also, our 3D printed shell are not yet durable for frequent bending, as essentially the structure uses impose a high stress internally, again leading to pretty bad failure cases, as you can see in this case, cracked devices. However, since the time of submission, we have worked on some of these issues, we have tackled them, and we have solved some of these. So we have developed a second MagTics prototype that basically tackled three main issues. Regarding the heat generation, we are now employing more efficient PCBs and more layers of them. So we are using 6 to 8 layers instead of 4, as it was before. As for the, you can see that. As for the heat dissipation, we now employ an aluminum case, which is more efficient in dissipating the heat than the thick rubber that we used before. And finally, for the 3D printed case, we removed all the unnecessary material used for the casing, but also the new prototype essentially has a very thin and rigid strip embedded into the soft casing that essentially keeps everything together. So with these improvements, we were able to reduce the energy required to operate our device. So at the moment, we only need short pulses of 40 watts. So we reduced this by a factor of 3. But also we reduced the heat generated. Actually, rather than the heat, we are now dissipating the heat much better right now. So the cooling time for our device in this with this new prototype has been scaled down by a factor of 10. So if you are interested in checking out the new prototype as well as the old one, I invite you to our demo this afternoon at 6 in a few hours. And okay, just to wrap it up, of course we are still working on essentially in future direction and improving our device. First of all, we are looking into more ways to improve the reliability of our soft case, and silicone molding, for instance, is something that we're going to be looking into for this. We also would like to increase the actuator density and count of our device, and this, of course, will go hand in hand with further miniaturization of the device. But also, as you can see from the video, we are starting to essentially experiment with 2D arrangement of our 1D arrangements, which already led to some interesting and promising directions. So this brings me to a conclusion, and I hope you enjoyed this talk. I'm now ready to take any questions together with my colleague Juan, which has worked for a very long time on the hardware. And thank you very much for listening.
Hi, thank you for very impressive work. I was wondering, I mean, the thing that gets me really excited about this is obviously the flexibility and the softness. And what I'm wondering about is if you were looking at different strategies to get more smoothness of these discrete locations, so either algorithmically through like sensor saltation or attaching some sort of skin on top. Like basically, what other strategies have you thought about to get a more of a analog feel as compared to these discrete locations?
Sorry, could you just quickly repeat the question? I don't think I got it entirely.
Okay, I'll try to compress it.
Yeah.
So in these prototypes,
yep.
I mean, it's really nice, like the flexibility,
yep.
But the feedback is on discrete locations.
Yep. Yeah.
So I was wondering if you had explored strategies in software where you maybe could create a sense of interpolation or through additional hardware on top.
And I got it. So essentially, one way that we could do this is basically playing with the frequencies of our actuation. So our frequency is actually we have a quite dynamic range. So it goes from 0.01 seconds all the way up to a second. So essentially, to get less discrete type of feedback, we could essentially interweave different type of feedbacks or actually play with this, if that's what you're asking, if that's what you're answer your questions.
Well, I'm also wondering, like, spatially between them, you know.
Oh, okay. Essentially, you would have to further miniature. Maybe Juan can answer this better. But
so to increase the density, you can place with some with the parameter of the design. But again, as like electromagnetic or voice coil actuator, when you start the force you can feel scales with the volume of the magnets of the elements you have there. So for now, as we say, the diameter of the actuator is about 1 centimeter. That gives the 200 millinewtons, 20 grams of force. But yeah, you can pay the price of lower forces and probably at higher frequencies that can be perceived and have more dense hardware. Yeah.
If there are no other questions, let's take